When you are given the information about an equilibrium system and you know all of the equilibrium values, you simply have to put the numbers into the equation to solve for the equilibrium constant. We saw that in one of our previous problems in our last video. And in this video, we're going to look at that. So and again, those are pretty straightforward problems. So for example, here in this example, they ask us to calculate Kp. So Kp again is going to equal the pressure of NH3, and we're going to square that over the pressure of N2 times the pressure of H2, and we're going to remember to cube that. So the pressure of NH3 is 0.166 squared over the pressure of nitrogen, 2.46, and then hydrogen, 7.38, and that has to be cubed. So I'm going to take 0.166 squared divided by 2.46 divided by 7.38 raised to the third power equals, put that in scientific notation for me, 2.79 times 10 to the minus fifth. Okay, now those are the easy ones. Now, many times they will give you some information and then you have to figure out the rest of the information before you can figure out the equilibrium constant value. Okay, now when you do that, you're going to use what's called an ICE table. An ICE table stands for initial, change, equilibrium. So you're going to you're going to make a table that has the initial values, the change values, and the equilibrium values. And I'll show you how to do that here in these next couple of examples. So in example 1, it says enough ammonia is dissolved in 5 liters of water at 25 degrees Celsius to produce a solution that's 0.0124 molar in ammonia. The solution is then allowed to come to equilibrium according to the following equation. Analysis of the equilibrium mixture shows that the concentration of hydroxide is 4.64 times 10 to the minus fourth. Calculate Kc, the value of the equilibrium constant, at 25 degrees Celsius for this reaction. So in a problem like this, the first thing that we're going to want to do is we're going to want to write the balanced equation. NH3, H2O in equilibrium with NH4 plus and OH minus. And then we're going to make a table. And we're going to put each of them into their own column. And we're going to write ICE, initial, change, equilibrium. Now, the first thing we're going to do is, since H2O is a liquid, its concentration is never going to change. We're going to go ahead and just put an X in there, just so we remember we're not worried about it. Now we'll go back to the problem and look at what the information that they provide us. So it says the solution is 0.0124 molar in ammonia and then allowed to come to equilibrium. Well, what does that mean? It means that before the reaction started, that was the concentration of the ammonia. Okay, and ammonia again is NH3, so it's the initial for ammonia is 0.0124. Now, what that also is telling you, that if initially there was 0.0124 molar ammonia, it means that there was no ammonium, NH4 plus, or any hydroxide initially, and this happens a lot, so you're going to put a 0 there and a 0 there. Okay. Now we'll keep going. Analysis of the equilibrium mixture shows that the concentration of hydroxide, so again, the equilibrium mixture, so now we're down here at the equilibrium, shows us that the concentration of hydroxide is 4.64 times 10 to the minus fourth. And that's all the information that they give us. Okay, the one part that we now need to fill in is the change part. And the change part happens by looking at your initial and your equilibriums and hopefully filling in those spaces. Okay, and so if OH started at 0 and now is at 4.64 times 10 to the minus fourth, that means it had to have gone up by 4.64 times 10 to the minus fourth. Now here's where you use stoichiometry. The change section is where you're going to use stoichiometry to convert all of those changes, because we know that if OH minus went up by 4.64, that's a 4 right there, 4.64 times 10 to the minus fourth, and for every one hydroxide, you get an ammonium as well. That means that ammonium also had to have gone up by 4.64 times 10 to the minus fourth. Which means that, again, if initially there was 0 and we added 4.64 times 10 to the minus fourth, then of course the equilibrium is those two put together. And then if these two both went up by 4.64 times 10 to the minus fourth, and there's one ammonia here as well, then it had to have gone down by that same amount, 4.64 times 10 to the minus fourth. And so for my equilibrium value, I'm going to take 0.0124 minus 4.64 times 10 to the minus fourth, and I get, and I don't need to put in scientific notation, 0.011936, and I'm not worried about significant figures here. Okay, and so now I have my equilibrium values. Once you have these equilibrium values here on the bottom, now you can calculate the equilibrium constant value. So the equilibrium constant is going to equal, again, look at our balance equation. Here are our products, NH4 plus and OH minus, and they're exactly the same. So I can take 4.64 times 10 to the minus fourth, and instead of writing it twice, I'm just going to square it. So squared, that's our products on the top, over water, don't worry about that, it's a liquid, and then 0.011936. So 4.64 times 10 to the minus fourth squared divided by 0.011936. I typed it in wrong. That's why it's good before you hit enter, and I hit enter too soon. Check to make sure your numbers are correct on your screen. And I get a final answer of 1.80 times 10 to the minus fifth. Check to see, make sure you get that same answer as well. Okay, let's do one more example here. Sulfur trioxide gas decomposes at a high temperature in a sealed container, producing sulfur dioxide and oxygen gas. Initially, so that's an important word there. Initially, that means that I part, right? The vessel is charged at 1,000 Kelvin with SO3 at a partial pressure of 0.5 atmospheres. At equilibrium, SO3 is 0.2 atmospheres. Write the balance equation, then calculate Kp. So first of all, sulfur trioxide is SO3, and it decomposes to produce sulfur dioxide, which is SO2 plus O2. Okay, so now we need to balance it. So we're going to need a 2 here. We're going to need a 2 here, and that gives us 2 sulfurs and 6 oxygens on both sides. So that's our balanced equation. Now we're going to have to make our ice table here, SO3. Oh, sorry, I didn't put an equilibrium arrow here. 2 SO2s plus O2. And let's go ahead, ICE. Nothing in here that we can cancel out, so everything's going to stay. Now, initially, the pressure is 0.5 atmospheres, so SO3 initially is 0.5. And again, that also tells us that initially, if they're only giving you one amount, that means that the other amounts must be 0, especially since they're products. Okay, and then it says at equilibrium, SO3 is equal to 0.2, so the same one, 0.2. Okay, and now we need to be able to fill in the rest. So SO3, what did it do? It went from 0.5 down to 0.2, so it had to have gone down by 0.3. Now we're going to look at the stoichiometry of the balanced equation. For every 2 of these, you get 2 of these. And yes, you can absolutely write it out. You can say, okay, the change is 0.3 for SO3, and then use that balanced equation. 2 SO3s makes 2 SO2s. So you can see that if this goes down by 0.3, on the product side, that one has to go up by that same amount based on the stoichiometry of that balanced equation. Okay, but O2, because for every 2 of these, you're only making 1 oxygen, instead of it going up by 0.300, it's only going to go up. Again, if you look at the stoichiometry, change this top one here to 1O2, notice that your answer becomes half as much, 0.150. So SO2 goes up by 0.3, O2 goes up by 0.15, and so at equilibrium you have 0.3 and you have 0.15. And now to figure out the value of the equilibrium constant, Kp is going to equal the pressure of SO2 squared. So that's 0.300 squared times the pressure of O2, 0.150, over the pressure of SO3 squared. So 0.200 squared. Okay, and so now I go to my calculator. 0.300 squared times 0.150 divided by 0.200 squared equals Kp equals 0.338. So as you can see, a lot of times they're not going to give you the equilibrium values like that first example did. They're going to give you some, and then you have to use an ICE table. And sometimes they call them RICE tables because the R up at the top stands for reaction. So you put the reaction on the top, then the initial, the change, and the equilibrium. I don't really care. I like ICE better, so I don't usually call it a RICE table. Okay, but some teachers will. Okay, so you can use those initial and those equilibrium values to calculate the change. And remember, the change section, that's where you must use the stoichiometry of the balanced equation. Once you figure out one of those changes, you use that balanced equation to figure out all of the other changes. Okay, and typically, certainly when your products start at 0, if they start at 0, these absolutely have to go up and these have to go down. And again, how did we know that this went down? Because they told us. They said this one started at 0.5 and it went to 0.2. So whatever side is going up, the other side has to be going down, and vice versa. In this case, the reactant side is going down, so the product side has to be going up. And again, almost every single time, the product side is going to be going up, the reactant side is going to be going down. But remember that at equilibrium, there's kind of that blurring between the what's a reactant and what's a product. Could you technically start with some product? You absolutely could. This could be 0.100. This could be 0.250. Okay, then again, well, are the products going to go up or the reactants go down? That's where you have to use the additional data that they give you to go, oh, wait a minute, well, certainly the reactant amount went down. So if the reactant amount went down, the product side had to have gone up. Okay, whatever one side does, the other side has to do the opposite.